Hey everyone, I'm Tyler Mandry, here with the Rust content team. I'm here with Michal, and we're going to talk about Rust and GPUs. So, to get started, Michal, just tell me the story of how you first got involved with Rust.
So it's actually a pretty funny story about how I started working with the Rust project itself on the Rust compiler. So I was using Rust to write a wrapper around the .NET runtime because I wanted to make a game engines that would use C# as a scripting language. And I had an issue. I needed variadic generics for a part of my API. I wanted to represent calls with a tuple of different sizes. Mm-hmm. And I found an issue in which there was a lot of bike shedding about the exact syntax, about how variadic generics should work. So I started working on an article. I was
there's bike shedding in the Rust community?
Yeah.
Weird.
Sometimes it happens. So I was working on an article, and I was like, well, who am I to say? Like, those very smart people that are bike shedding probably for a reason. There's a high chance I'm not understanding what the problem really is. So I was like, I should probably start working on something related to the Rust compiler to actually understand what I'm talking about. So I started to thought myself, what I'm working on right now, well, something related to .NET. What if I could compile Rust to .NET and create a throwaway prototype to actually understand how the Rust compiler works? And then people liked what I was doing, and an article I wrote about this, and it kind of spiraled. I just kept going with what I was going with a prototype that originally was just a silly idea. We have a saying in Poland that loosely translates to trying to attack the sun with a hoe. So I would say that a lot of my endeavors kind of like that. I'm trying to fight the sun and other planets with some very inadequate tools.
So did you end up writing the article about variadic generics?
No.
No.
It's still somewhere, I think, either on my disk or on my GitHub. It's a terrible article now in hindsight because there is a reason I didn't release it, because I didn't understand the problem. And knowing what I know now, I would have probably only added to the bike shedding. But one good thing about all of those, I think it was something about 3 dots being used in the variadic generic template. So one good thing about all of that bike shedding was that it got me into Rust. I got so annoyed by people bike shedding, I decided to throw my hand in the ring and...
That you decided to join the bike shedding?
Yeah!
Okay, well, yeah.
And now I'm here.
If you can't beat them, join them, I guess.
Yeah, life goes in really weird and different directions.
So tell me more about that experience of actually getting involved in the Rust project, and how did you meet people? What was that interaction like for you?
I would say that a lot of the people on the Rust project are very, very friendly, which was very great for onboarding as a newcomer. I have come to them essentially with I'm working on something very stupid and silly. I need help. And the fact that I actually received help and feedback, that was very, very great. And a lot of the Rust community, as I said, was very encouraging under my post. And seeing people actually like what I write, people actually really liking the technical content, it really helped me feel like I can contribute something in this community. So this has been great to me. There are some things obviously that have been issues when I was starting, and are still issues. For example, the Rust compiler documentation is very bad still in some places. There's this may be outdated, but there was a function called mkplace, which the description just makes a place. Mm-hmm. And what does that mean? I think that that particular function, it was something related to the way we represent things like field access and references overall places, and I was confused as to what one of its arguments was doing, and I couldn't tell from just reading the documentations. I actually had to read the code base, which was a bit annoying. So I feel that's one thing that as the Rust community we could improve, because the documentation of the standard library is stellar. But the documentation of internal tools, I have discovered so many cases also outdated documentation. There's a format for embedding Rust metadata in shared objects that I found a description for it in the documentation, but it turns out I found a description version 6 and we are on version 21. I found a description of a complex compression scheme, and that it's no longer compressed. So there are places where we definitely can improve, but even here, one of the biggest things I noticed last week is just how many different places people have come here. So many very, very different people, which all work together on one project. And I think that's kind of beautiful and really shows, this may sound slightly silly, slightly lofty, the potential humanity It's like when we all work on something together, despite our various differences, we can achieve some great things. I have met some friends whom I could have never met else without Rust. I have met like a friend from Canada that's so far away. I would have never ever met that person without Rust.
Yeah.
And it's a pretty valuable friendship.
Yeah, and now you're here at RustWeek at this conference, and yeah, I mean, I can definitely relate to that experience of meeting people, you know, at Rust conferences, and
It's also pretty silly to see the difference between how you imagine that person and how they are. Like I obviously I haven't heard the voice of some of those people I know, so I had an imaginary voice in my head, and I'm like, no, you sound nothing like my idea of how you should sound like.
I've had that same experience. Yeah, absolutely. Especially when it's like a handle and it's like a Gravatar handle, and so you've never seen this person's face or anything. So we'll get to GPUs in a second, but I know that you were working on like alternative backends for the Rust compiler. How did that happen?
So all of that like started with that silly variadic generics and me creating like a backend to compile Rust to that .NET bytecode. I was working on it for like a year, and then like someone suggested to me like you should apply for Rust GSOC, but I was a bit afraid that my
GSOC as in Google Summer of Code.
Google Summer of Code. Yeah, so I was afraid that actually something related to .NET like it was too niche to actually get a mentor. So I started considering turning into Rust. I was like, I saw a proposal for a Rust C compiler. I was like, how difficult would that be to do? And I started modifying that code base, which was targeting .NET, to actually emit C, because I had a representation for like .NET bytecode that was tree-based. And I was like, well, a tree can be turned into an abstract syntax tree, and I could emit C source files that way. So it was a very minimal, like 2,000 lines of code to make it also emit C. But then I was encouraged to actually keep with the .NET. I have made some silly mistakes along the way when we are searching for the mentor. I'm actually a reason why there's a rule or like a guideline added. Please do not like cold call mentors, because I was messaging people trying to find anybody who would be willing to help me with that. It was very embarrassing, like in hindsight. Oh, yeah, it was probably not a very good idea. But at the same time, I'm very glad that I tried, because once again, I got to meet a lot of really amazing people via like work on the Rust compiler.
Yeah.
And I'm here when I'm where I am because of that work.
Nice. Yeah, I think it's such an interesting approach too of having. I mean, basically, you're kind of doing interop with this alternative backend, and that lets you call between Rust and .NET code, right? And Rust and C code.
I think like the people who are who actually know how Rust C works, they would be horrified about some of the things I have been doing there, because I have been representing, for example, I needed like some way to pass, for example, class and function names when I'm trying to call a virtual function in .NET. So I had a function called Rust C cogent CLL virtual call, something like that, and I used const generics to represent the names of the actual function I want to call and things like arguments. So I had a parser that would extract const generics from the on the instantiation time. It was like a crazy piece of tech for like. I also had something that would pass like constants to create .NET type class definitions. So I had like a whole complex system where I was kind of abusing the Rust type system to sneak in some metadata for the backend.
Sounds like some mad scientist.
It's mad science stuff, and it will probably break. But oh well.
But it's cool. All right, let's move on to GPUs then. So I'm very much a novice when it comes to GPUs. Like my idea of what happens on GPUs is like you write some shader code, and then that like I don't know colors your textures or something. But like you're working on allowing Rust code to run on a GPU. Rust is obviously a general purpose language. It's not a shader language. Like, what are some reasons that you would consider actually running Rust code on a GPU?
So there are two different angles for this. The one angle is I want to write the code that I was usually writing for GPUs in Rust, and the reason there is like GPU code is usually in a kind of dialect of C++ in CUDA, and that's unsafe. And there are some kinds of like issues. I, for example, talked to some people who have told me that they found like a data race, and like 1 in like 5,000 GPU hours they would get incorrect results due to like a data race, and that was very annoying to catch. And this is like a place where Rust could help, because Rust is very explicit about safety, synchronization. But there's another angle, and there's an angle of we want GPUs to be able to do more. We want to be able to bring a general Rust program to a GPU and have it accelerate that. So GPUs have a lot of threads which can run in parallel. For example, I had an old CUDA laptop which I think could support up to 13,000 threads running all at once. So those threads were slow. I think for that laptop, I measured it to be like loosely equivalent to like an old Pentium. But like once you have 13,000 old Pentiums, you can do some pretty cool stuff with them.
Okay.
So there are those like the two prongs, and I feel like the tension with my work and with like all of the work I'm doing at VectorWare is like we want very much to move to like the future stuff, being able to run more general code in Rust. But there's also a question. It's like more so an experiment. We know that we can already write normal GPU code in Rust, but we also want to be able to run normal Rust on GPUs, and that's difficult, but that's why I love what I'm doing, because it's difficult. And as I said, I love fighting the sun with a hoe, this metaphor.
Yeah, so now you're working on a backend for a GPU rather than a backend for the Rust compiler that emits GPU code, correct?
Well, I am one of the maintainers of Rust CUDA, and this basically, once again, a Rust compiler backend, but it emits something called PTX, and it's an IR for NVIDIA GPUs. So actually, your driver will ingest PTX and will turn it for GPU native instructions. So that's one of the things I'm maintaining, but I'm also doing a lot of, for example, the SCD on GPU example that requires things far outside of the backend. Actually, the backend is really not relevant to all of that. What's relevant is the changes to the Rust standard library and the underlying runtime. We have like a wraparound CUDA, which is responsible for like all of this magic, let's say.
Okay, tell me about that. How does actually getting the Rust standard library to work on a GPU? What does that?
So basically, the core idea here, I wanted to start like thinking, how can I open a file from a GPU? How could I read a file from a GPU? And I thought, well, a GPU in itself cannot do that, but the GPU can do some things. It can, for example, write to memory. And I thought to myself, well, there are some protocols based on like shared memory, for example, remote procedure calls. So what if we use kind of FFI over RPC? So what if the GPU writes a bunch of data which is interpreted by the thin CPU wrapper to like execute some syscall and map some file into GPU memory? And this is kind of how all of this works. We just have something called the host call layer, as the name suggests, host call. You can call the host, the CPU host, from the GPU guest. And we serialize this data into this piece of shared memory, and we can use that to do more or less arbitrary FFI. So we have like a trie that allows us to serialize vecs, strings, paths. So just all of this gets right into a buffer, and the CPU just asynchronously executes this for a GPU. So we can like schedule, oh, please open this file to me, and we have a handle to something that the CPU will inform us, oh, I am done with this work.
When you say serialized, do you mean according to like the memory layout defined by the host and the target layer, like the native memory layout, or are you actually using some kind of standard?
We have like this protocol is, I would say it's most like the way CRD serializes stuff. We have like a format byte for byte that's like, it's optimized specifically for GPUs because GPUs are kind of weird. Originally we actually didn't do serialization, but we just write, for example, a raw pointer. But the problem with that is that GPUs have a set of like complex address spaces, and only some of them are accessible to a CPU. So by forcing serialization, we could make sure that actually all of this data is stored in data that's accessible in memory that's accessible to the CPU too, and we could also avoid a whole class of errors. So it was kind of a trade-off. Do we want like a simple protocol, or do we want a protocol that's more robust? I actually had to rewrite everything from like the first prototype because I learned a lot. I was still naive about GPUs.
No, that makes a lot of sense. I mean, you don't have an actual shared, unified memory between the two necessarily, so you have to.
Yeah.
write everything out that you need.
Yeah, it's slowly going towards that way with more and more devices having unified memory, but it's not really something we can, even with unified memory, like there's something called CUDA shared memory. It's basically a tiny bit of memory wired to a CUDA core, and it's very fast to access, so that's why people might want to use it. But it's not accessible to a CPU, like it's wired physically to a core. Originally, I believe it started as a piece of cache that you could say, oh, this is not really cache, this is a piece of fast memory I want to use.
So I was actually going to ask you how how the architecture of GPUs differs from CPUs.
So I would say it doesn't. If it's both more different than you may imagine, it's more similar than you may imagine. Kind of a non-answer, but I would say the main difference is that there is a lot of things we cannot kind of puncture through in GPUs because we have to use those layers above. On the hardware layer itself, for example, we just have normal instructions which are very similar to what a CPU exists. So it still fetches data, it still has registers, all of that. Okay. But for example, CUDA has something called the local address space. And this is, the thing about it is that it's thread local, and you place the issue with it is that CUDA places the stack there. So you cannot send stack references to another thread, and this is like something that breaks semantics of Rust. And this is something we really cannot directly puncture to, and something that we have to kind of work around. So I would say the biggest difference is individual GPUs cores are slow compared to like all of there's a lot of slow things. Like I would say equivalent like a factory. If you have like a million people working in a factory, even if they do have to do math by hand on paper, they will be faster than a person with a calculator. But if you have to do if like latency and things like that matter more, then they are not as fast. So I would say those are the two big differences.
Yeah, that makes sense. So how do you, that's so interesting. So if the stack is only accessible to that particular thread, how do you work around like the fact that Rust just allows you to?
So that's actually kind of part of the topic of my talk. And currently, we have actually spent I spilled a lot of ink trying to figure out a way to expose this Rust in Rust in a way that would be sound. Like how there's a thread in our work slip on like, oh, what can we do this? How can we make a design for other spaces in Rust that would work with this? But I couldn't really get it to work. So in the end, the solution is just like, screw the CUDA stack. We'll allocate our own stack in global memory that we know is accessible. Mm-hmm. This is like very much fine for what we are doing internally at the company because, as I said, we already have our own wrapper around runtime, so we can have that wrapper do that. The issue is more so with other people who are writing CUDA code without wanting to use that sort of wrapper. I believe, like don't quote me on that, but I believe we plan to open source that wrapper, but we still cannot expect really people to always use that. So we have a way to make Rust on GPU sound, but we have to kind of encourage people to use some of the stuff we are building. So that's the primary issue, that people who want to use this with stock CUDA, they would have to also allocate. The fundamental questions like who is going to allocate that stack? We can say with our own work, like we have a runtime, it can access a runtime wrapper, it can just always allocate that stack for us. It can do some smart stuff like pull the stacks.
Okay. Yeah, that makes sense. So you gave a great description, I think, of why you might want to use a GPU. So you know, if your code benefits from a lot of parallelism, and we know Rust is very good at modeling parallelism in a safe way. If it doesn't need good single-threaded performance, because like you said, a bunch of Pentiums. What are some other reasons that you might want to avoid a GPU? Like,
so I would say one reason is just like a lot of this tech is just not ready. Like I'm working on it. It will take us time to actually get where we want to get. There's a lot of thought in us. Like we are thinking about like what are the reasons we would like to avoid that, and we are trying to mitigate them. For example, the fact that, obviously CPUs are faster at single-threaded performance, but there is a question like, what can we do about it? So I mentioned unified memory. So the cool thing with unified memory is that we could have both GPU code. I had like a prototype that would expose all of the CPU memory to a GPU using unified memory. So this way you could run both GPU threads and CPU threads in the same shared memory. They would still share. You could, for example, call host side malloc, and they could share the same malloc heap. So it would all be identical. They all use the same pointers, the same addresses. And
is that supported on all architectures, or
it does require you to have like some specific newer GPUs, but like I think like the problem really there is like, oh, do you? This is like supported for modern GPUs. So the question is like, do we really want to support something like old GPU from 2014, or do we just want to build more modern software? So I'm personally leaning into the direction of like we can just drop support from some very old things because they will be slow anyway. And if we kind of make those requirements higher, we can actually do some really, really amazing stuff. Like I would say that one very hard thing about this job is knowing that we have more internally that we are showing externally. And there are some things that I would absolutely love to talk about because they're very, very, very cool, but just not yet.
All right, well,
It's
stay tuned.
annoying.
All right, so yeah, does a GPU have? You model it as as like a Pentium. Like, do GPUs have branch prediction? Like, are they good at doing any kind of random access? Or
the focus there is more so at throughput, and GPUs do something because normally with like branch prediction you are trying to lower latency. You want to avoid stalls and you want to avoid wasted cycles. So GPUs do something clever because when they are stalled, for example, waiting for memory, they know, oh, I have to wait for 100 cycles for memory. So they have something called warps, and they have a lot of those warps in flight at once. So they can switch from one warp to another.
Okay,
so,
it's kind of like hyper-threading.
Yeah, so it's basically like very wide hyper-threading, and if something is just waiting for the memory, you can just switch. Mm-hmm. And because this is like, this kind of depends on how many registers you use, actually, because the hardware is physically limited. But because a GPU can very quickly switch between those workloads, I think in a cycle or two, the latency is really not as visible. So really GPUs trade away the latency for throughput. So the throughput is not wasted, but you are just sometimes waiting slightly more on an individual task.
Okay, interesting. So you've been working on getting like the standard library to actually run on a GPU, which is very cool. Yeah, sounds like you're working on a bunch of other things at your company. Walk me through the process of like actually getting that working. What was hard about it?
Oh, lots of things. I would say the biggest issue is like, it's something I always face my projects when I'm trying to do something C, like compiling Rust to C. Normally, like you have people who can like help you a lot with this, but for example, there are not a lot of people who are experts in Rust compiler and GPUs. So I kind of have to do, if I find a bug, I sometimes just have to spend the time minimizing the bug myself. I can't really get any help. So I had, for example, a setup where I would go to sleep with like C-wise minimizing a bug reproducer. So I can then later I had, for example, I don't know, 40,000 lines of code that I know there was a bug somewhere, and then I would wake up in the morning and it was still running, trying to actually find where the bug is. So I would say, at my company, there's also a split between like some Vulkan people, which are like for the Vulkan is kind of our fallback outside of NVIDIA, because NVIDIA is currently very dominant in the GPU field, as I think most people know. We still do want to be able to support other things. We don't want just to be like be like a CUDA workshop. We do want to be GPU people. And the big issue is that there are not a lot of people who can really handle this, and my bugs I introduce are my bugs. I have to work on them myself. So I'm kind of wearing multiple hats. I'm both the person using and the person who is producing what I'm using. So I can't really yell at someone that their stuff is broken.
Yeah, this is a classic problem in compilers, I would say.
Yeah.
Cool. So what would you like to see happen with this work in the future? I know you said there's things you can't talk about, but what can you talk about?
So I would say I have some pipelines. Ideally, I want to be able to run as much Rust code on a GPU, and I think some very cool experiments would be stuff like Tokyo and stuff like Rust C. And I'm thinking because a lot of people complain about slow Rust compilations, I was thinking what would, with 13,000 threads, even if they are slow, I could probably outpace a CPU on my laptop, on a modern CPU on my old kind of dilapidated laptop. I think I got it for my birthday some years ago, and I think that's like one of the things that Rust is enormous, like the compiler, and getting something that big to run, I would feel like I'm accomplished because I have like achieved my goals in life, because there is like once I know that something that big runs, I know that kind of we have won, we can run anything on a GPU.
That would be really cool. And I mean, you could, to your point earlier, I mean, you could split it up and run some things on the GPU and some things on the CPU. That would make more sense.
There's
you do
like
borrow checking in parallel or something. And
there's a lot of like work in this whole area of like how we can squeeze all of the juice out of a GPU. How can we make sure, or for example, cases where you have multiple GPUs, how can you schedule all of the work around so that they maximize the throughput? It's like one of the great things about RustWeek was also that I get to talk to a lot of people who also use both Rust and GPUs, and I got to hear some stories about like how they do stuff and how their issues. And this also like kind of helps me put some things into perspective, like what we should and shouldn't really care about all that much. So it has certainly been enlightening.
Yeah, that makes a lot of sense. Well, this is really interesting to hear about, and yeah, I'm looking forward to hearing more about what comes next with Rust and GPUs. Thanks, Michal.
Yeah, I must say, good things are coming. Just wait. You have to be patient.
Awesome. Thanks a lot.
Thanks.